Hello. In the previous video on gravitation, we had discussed about the gravitational field and the field intensity and the Earth's gravitational field intensity, which is actually the acceleration due to gravity that we have been using in various calculations involved till date. Now we shall discuss about the gravitational potential. Now, from the term that we have potential, it expresses that how much is the gravitational field that is surrounding a massive object, how much is it capable of providing any kind of work for the gravitational attraction or the force of gravitational attraction uh, acting on any object and thereby moving it or attracting it towards itself, because the gravitational force is completely involved with attraction. So to begin with, about the gravitational potential, how do we really calculate it? Because it is associated with the work that is being done, and we express it as the work being done by the gravitational field per unit mass. Let us assume that we have a mass m, a certain mass m, and we wish to obtain the work that it does in order to attract a smaller mass m when it is being attracted from infinity to any point which is lying at a distance, supposedly say r. So this is the mass m, and from it we have a point which is lying at a distance r. This is exactly the way we had calculated the electric potential, but in that case you can have the work the other way around, where the work is done by a system in order to bring the charge, but here the mass is being attracted by the mass itself, because the gravitational force is attractive in nature only. There's no repulsive case over here. So if it is dragged up to a distance, let us say x, then the force that exists at that point is simply g m m divided by x squared, and from that, as it is moved through a distance dx due to the gravitational field, remember the gravitational field here is acting towards the object in order to attract it towards itself, so the direction of the force is along the direction of motion, and that is why you have the dot product. In order to obtain the work, dw amount of work is done to displace the mass m through a distance dx. So what we have is f dot with dx, and in that case the force and the displacement are acting along the same line, and so you have cos 0 over there, which is obviously equal to 1, and the total work thus done in order to drag it from infinity to that point in consideration has to be integrated, and that is integrated from infinity to the point in consideration which is at a distance r. We want to place it at the point P, which is lying at a distance r. So in order to obtain that, we just integrate this term. So this is gmm, and x squared, that is x to the power minus 2, is simply minus of 1 by x, and that is from infinity to r. And what we have finally, the minus sign can be taken outside, and what we have is the upper limit minus the lower limit. Now 1 by infinity simply goes to 0, and what we have is gmm divided by r, and this negative sign shows that this work is done by this system, that is the capital M mass, and the small m thus is being attracted by it. So this negative sign is what the potential tells us about, but the one thing that we would like to bring to your notice is that we are concerned about the potential. So this work actually is stored or is given out in the form of potential energy, And this gravitational potential energy that we have over here, gravitational potential energy, the work that is done or the potential energy invested per unit mass is what is going to give us the gravitational potential. Usually it is denoted by the symbol V, same as in case of the electrostatic potential. But nevertheless, the denotations that have been given have been mentioned, so there's no problem with that. So this is simply gravitational potential that we have started this video with, and giving it per unit mass. So what we have is gmm divided by r is the value of u divided by m. So the m can get cancelled out. So this gives us the potential of the capital mass M at a distance r, that is its capability of bringing or working the small mass into that particular point. And so this gravitational potential at this is the gravitational potential at a distance supposedly r from the given mass. Now there are various type of objects which can consider, and we can obtain the gravitational potential with associated with those kind of mass distributions. There are linear mass distributions, there are superficial mass distributions, as well as cubical distribution, that is the distribution throughout the entire volume. So let's just get started with that. So first up, we have the linear mass distribution, where the mass is distributed mainly over a length dominant object. Let us say in case of a ring, a circular ring that we can consider. So we wish to obtain the gravitational potential associated with a ring. Now it's just not associated, but the it's at a distance, let us say at an axial line, along that axial line of that ring. So this is the ring, and we wish to obtain the gravitational potential along the axis. In order for that to happen, what we need to do is first we need to know how the mass is distributed. Now as the mass is distributed uniformly, so we have a certain mass for the ring, let us say it is m, and that is distributed over, let's say the radius of the ring is supposedly if we are taking this as r, let us say the radius is simply let's take it as a. So we have 2 pi a. This is a length dominating structure or body. So the ring may have a certain thickness, but that is very negligible in comparison to its circumference or its overall length. So we are just concerned about the mass distribution over that length. So this is 2m divided by 2 pi a, which is the circumference of the ring. Now we can consider a certain element, let us say of length dl, right? We are considering a certain smaller element of length dl, which is selected right there, and that dl element will obviously have a smaller mass which will be equal to the mass per unit length multiplied with that length. Let us say this is some small mass dm. Now the potential at a distance r from the center of the ring, of the given ring, will obviously be along that will be due to that line from that elementary length, so for that elementary length that we have considered, which is carrying a mass of dm, what we have is the potential is a small potential, that is dv, which is equal to minus g times of dm divided by r. Instead of r, we have this length over here, And what is that length? That length obviously is a squared plus r squared under root, or just to the power half. And then we just integrate this thing over that entire length, over that entire circumference. And so what we get is simply the result as it can be seen, although the result looks quite ordinary and could have been obtained directly. But what I insist on doing is that this method will be useful in various other shapes and various other mass distributions we are about to consider. So it's quite legit for us to take this kind of an approach, which is going to be the procedure for the rest of the cases as well. So I take the constant terms outside because a and r both are constants. The only thing that is variable is dm, which is now, as we know it, as m by 2 pi a times of dl. So L has to be integrated from 0 to 2 pi a, which is obviously going to give us 2 pi a, as simple as that. So gm divided by a squared plus r squared under root, and that 2 pi a that was there in the denominator, that gets cancelled out with the 2 pi a minus 0, which is obviously 2 pi a. The integration gives you 2 pi a, and there is 2 pi a at the denominator. So all that you are left with, let me write it over here, v is simply now equal to minus of gm divided by a squared plus r squared under root, or to the power whole to the power half. So this is the expression for the gravitational potential due to a linear mass distribution, that is in case of a ring over here. Now remember, the potential that we have is a scalar quantity because it is obtained from the energy or the work that is done in order to bring the charge. So work being a scalar quantity obviously gives us the potential to be a scalar quantity as well. And what about the units that is involved? Now in case of gravitational field, obviously we had it to be meter per second square, as in case of the gravitational acceleration due to gravity, that is g. So that is why this term that we have is field, this is a work done per unit mass, so this is simply joule per kg. This will be in joule per kg, is the work done per unit mass. So now moving over to the next bit, that is for a surface charge distribution, that is let us consider the case of a spherical shell. You can also consider a disk, complete disk. But actually in case of disk, I leave it to you. You can use the concept of ring over there. Okay, let's just start with the disk, and I'll be giving you it as a task to try it yourself. What happens in case of a disk is that in case of a disk, you have the mass to be distributed over that entire area of the disk. Let that disk also have a radius of a, and so you have the mass to be distributed over that entire area, and so this mass is distributed over pi a squared, and so the mass per unit area is simply pi m by pi a squared. Now what you have to do in order to obtain it along that axis, here again we consider the axis, so along that axis, in order to find the gravitational potential, what you need to do is you just need to consider a ring over here, which we have just obtained the expression for, and that ring supposedly is having a radius of x and has a thickness, in this case being a dx. Although it has the thickness, nevertheless you can consider the thickness to be negligible in terms of the complete circumference. The thickness in this case over here is simply dx. thickness is dx, and in that thickness the mass that is contained in that is equal to, well, the area in that case is simply 2 pi x times of dx, because if you just cut it from one end or at one point and just get it as a rectangular strip, in this case it will be like this, a rectangular strip of thickness dx that we have just considered, and that rectangular strip will have a length of 2 pi x, that being the circumference of the circle, and the thickness in that case is simply dx. So dx times of 2 pi x is what the area is, and because the mass is distributed over this entire area, so this will now have a mass per unit area pi a squared times of 2 pi x dx, right? And with that mass available, let that be equal to dm, we know that this will be at a, this is x squared plus r squared under root, so this will be the distance, and thus you have a small gravitational potential due to this small elementary strip, that is equal to minus g dm divided by x squared plus r squared under root. But here's a twist. The thing is that you have to consider this dm now, having the case that this is pi a squared and this is under root x squared plus r squared, and 2 pi x dx, you have to open it up, because the thing is that you have an x over here, you have an x over here, which are variable terms. So what you need to do is you have to integrate with those terms available to you, and then you will have the value. So I leave it to you. I'll stop it over here, and I'll because we'll be dealing with this later on as well, probably if not in this video but in the other video for sure. But I'll just ask you to try it yourself so that you have a practice of the integration. And this integration, obviously x is integrated from 0 to a. There's nothing really big about it. It's quite simple, but I would suggest that you try it yourself. And then we move over to this. I'll keep it till here. Then we'll consider the case where we'll be considering a spherical shell. And as for this previous case, I can leave you with an answer for this for sure. The answer to this one will be somewhat like v is equal to minus 2gm divided by a squared, and with that integration that is involved, what we get is a squared plus r squared root over, because this is the entire radius is a, and remember this part is simply x, which is extending from 0 to a, and this minus r being that axial distance. So this is what the potential at this, in this case, looks like, but however I have left it to you for trying it. However, if you are unable to do it, you may comment it and I can help you out with that with a video or so. Now this is easy integration stuff, you can try it. So with the spherical shell that we have at hand, this is supposedly a spherical shell which is having, again, the mass is uniformly distributed over that area, and this does not look like a shell though, spherical one, but I'll try to draw it perfection, which is not the case with me most of the times. So now we have the center of the sphere. This is a spherical shell, so the mass is distributed over the surface, that is 4 pi, and here again the radius, let us consider it to be equal to a. So this is a, and 4 pi a squared, and that has a mass m. So for a unit area, the mass is m divided by 4 pi a squared. And well, for uh, in order to consider at any point which is lying outside the sphere at a distance supposedly equal to, we can keep it as r every time that we have, and this point is P, as was this point. And in that point P, we wish to obtain the gravitational potential, and for that we can consider a strip, circular strip over here, which is of a certain thickness now, and that thickness will be taking it in terms of the angle now. This is another approach to such a problem. Now this angle, it is obviously for that small strip that we have, this angle is very small as well. That's elementary strip. That angle is a d theta, and this entire angle is taken at an angle of theta. And with the radius being equal to a, and the angle subtended is d theta, so obviously you have this arc length to be equal to a d theta. Now a d theta arc length, and the radius, however, at this point is somewhere over here, considering it three-dimensional case. This was the entire circular, and this was the outer rim of the circular strip that has been considered. And that radius here is obviously not equal to a but less than a, so it is simply a sine theta. So that a sine theta, let me draw it pretty clearly for you. So this is that strip that we have considered. This certainly has a radius, and that radius being the component of the given radius, that is a sine theta. Why? Because this center, from that center you had the distance to be a, and obviously this is a sine theta with this angle being theta, right? And the angle that we have considered for that strip is obviously that angle d theta, which is within that within those two lines. So this is a sine theta now, and from that point, from this point on, we will be obtaining, now this is lying at a distance, now it is not r obviously, this distance that we have considered over here, now it will be obviously less than that, because this distance is a smaller one, of course. Let this line that we are taking, let us name it for now, let us name it as a z, suppose, and we are having a sine theta over here, and this entire length is r from the center. Now with that available to us, what we can do is we have a triangle, and in that triangle what we have is the angle between two vectors giving us some resultant z. Z here can be treated as a resultant for a and r, while a vector is this one, the position of that point, and r vector is obviously the position of this point P, which is lying outside the sphere. So z here can be taken as along this direction. Z gives you the position of the point P with respect to this upper point. Let this point be, suppose, I cannot take it as M, I can take it as some other point. Let us say this is point P, this is P dash. So with respect to that point P dash, the point P now is having a Z vector. Now A plus Z is definitely going to give us R. But what about Z? Z on the other hand is equal to A vector uh, R vector minus A vector. Simple uh, triangle law. And with the angle involved, let this angle, let us say that is theta over here. The angle over here is theta, of course. So A and Z and A and A and R do have an angle between them which is equal to theta, but there's a negative sign over there, so that means as per the triangle law, what we have is Z square simply will be equal to R square plus A square minus, because of that negative, the vector negation, that is 2AR cos theta. So this being the value, now as it is that we have this value Z over there, we'll be just wanting to obtain this area of the strip. First of all, the area of the strip in that case is simply A d theta, that is its thickness, multiplied with the entire circumference, which is A sine theta. A d theta times of A sine theta. A d theta is the thickness of the strip. A sine theta is its radius, so it is 2 pi times of A sine theta. 2 pi A sine theta, which obviously gives me 2 pi A squared sine theta d theta. This is the area, and the corresponding mass, let me write it over here. So for 2 pi A square sine theta d theta, the corresponding mass will be mass per unit area, that is 4 pi A square, multiplied with the area 2 pi A squared sine theta d theta. And this pi a squared, and with the 2, another 2 goes out, so what we have left with what we are left with is m by 2 sine theta d theta. This is the mass of that elementary strip that we have considered of thickness a d theta. Now we have this equation, right? In this equation, what we get is, if we are to obtain this the derivative of this equation, then what we get is, we just differentiate it. The point P can stay over here. 2z dz. R is a constant because it's fixed. A2 is a constant. And what we are left with is 2AR, and for that cos theta we have minus sine theta. Now minus sine theta multiplied with this minus before that is simply going to give me sine theta d theta. So sine theta d theta. So this is 2AR sine theta d theta, which is equal to 2z dz. Now the 2's can be taken care of, and simply we have the value of sine theta d theta, and that value here equates to z dz z dz divided by AR. This is the value of sine theta d theta, which we can put over here. So the dV that we'll be getting, let me take it to the next page. The dV that we'll be getting will simply be equal to minus of G, because this is in the form of a ring, so G times of dm divided by that. In case of the ring, we had this hypotenuse, which we were using a square plus z square, a square plus r square under root. Instead of that, we have just put a z over here. If you remember, instead of that, we have just a z over here. So just to make things easier for us, so we have to put that z over here. And in case of dm, now what we have is dm was equal to m by 2 sine theta d theta. So we just put it over there, minus g divided by z, instead of m by 2 sine theta d theta, we have the m by 2 for sure. But what about the sine theta d theta? As you know, that is going from that is z dz divided by we had obtained it over here, like right there. Sine theta d theta is simply equal to z dz times of ar. So z dz divided by ar, not times of ar. So this is the value of dv, right? And we can keep this value and we can integrate between different points, obviously. If the point r is greater than the radius, now r, for r greater than a, what we get is we integrate it. Now as we integrate, obviously this is the sphere shell, and we have the radius as a, and there's a point which is lying outside it, right? And in that case, what we are about to integrate over a z. Now z is something like this, it is going like this, right? So as we are integrating, how do we integrate z? Now z goes from here, you take those spherical strips starting from this point onwards, and you keep on integrating them up until you reach the other end, right? So in that case, z is simply varying from this distance to this entire distance over here, this end. So how is z changing? This center point distance was r, and sorry, it got overlapped. This center point distance was r for that point, and now this one was a, the radius, that is. So this length initially is simply z, or let's say r minus a, and as it approaches with these strips up until this point, the distance now is simply r plus a, right? So all that you have to do is you have to integrate this term that we have over here. Dz is getting integrated from r minus a to r plus a in order to cover the entire length of the shell, when we are, that is when we are considering the point to be outside the spherical shell. So now as we integrate it, what we get is v is equal to the integration of dv, which is equal to simply the minus gm by well, if you observe clearly, the z's obviously get cancelled out over here. I forgot to do that. Gm by 2 ar, that stays out, and what remains is dz, and that is being integrated from, as I said, r minus a to r plus a. And as that happens, what we get is simply dz is integrated to z, and so we have v to be equal to minus gm divided by 2ar, and dz is simply z. We can just write that directly now, as you might have understood this. I hope you have. So the process of integration, I'm not going stepwise now. So minus gm divided by 2ar, and what remains over here is simply the r and r get cancelled out. The minus of a becomes plus of a, so we have 2a over here. So 2a and 2a cancel out, and simply for the shell, surprise surprise, we have just gm by r, as simple as a result as that. But obviously the process was quite tasking, as we had to integrate it through a whole range of things, and we had to consider a whole range of things. Well, what the process obviously took a lot of thinking and time, but I really insist you that you go through these processes so as to get a clear picture of the procedures that are involved in such calculations. It will help you to calculate things in a better way, of course. Now, as for the distance lying within the shell, if we are to obtain the potential within the shell, what we can do is just change the limits in this case. Now, as the limits were from r minus a to r plus a, well, for a shell, for a point inside that shell, as we have this point over here, let us say we are going from this end to this end, and that is how z is varying. Now z over here is for these strips, remember, and these strips will go from one end to the other, and in that process what happens is that here, r being less than a, the limits are just reversed, where you have the limit ranging from a minus r to a plus r. Now what happens is that as you had r minus a and r plus a over here, you were getting 2a. Similarly, for this kind of an approach, what you will be getting is, obviously you can answer it now, it will be 2r. And so instead of those two a's cancelling out over here, now you will be having 2r cancelling out, and finally the expression, as you know, will be minus gm divided by a. So that's inside the shell, and obviously on the surface you will be having gm by on the surface you will be having, well, I'll leave it to you, you can try it for yourself. Now this variation obviously gives us, well, let me just give you a hint. What happens is that the r over here that we have obtained, this r value changes as per the point taken. That is, I can take the point over here, P. I can take the point somewhere closer as P, and so the distance of r is variable and is as per our choice. But as the r goes inside this, what happens is that this thing that we have obtained over here, that gives us a constant value, which means that the potential remains completely the same right from the surface and inside. So the task I was trying to give you is the one that I have solved myself. That is, on the surface the potential will be gm by a, and it will continue to be the same within the surface at any given point. So in case you are to obtain or give a graphical representation of it, so you can give it graphically as here this is the negative axis, of course, so this is simply minus gm by a is the negative value, and this goes the same till the radius, that is for a distance a, and then this value is the same, and then it starts falling off and exponentially, of course, as 1 by r. So obviously it approaches the towards the positive axis because the negative value goes on decreasing. As r goes on decreasing, the negative value uh, as r goes on increasing, the negative value goes on decreasing, and hence you will approach the positive axis. But nevertheless, it will remain negative every time up until infinity, where it is zero, which is obviously uh, given by this asymptotic nature of that curve. So this is the variation of the potential, gravitational potential, with respect to the distance from the center, or yes, from the center of the shell, within the shell, on the surface, and outside it. In the next videos, we'll be trying the volume mass distribution, and thereafter we'll be considering the relation between the gravitational field and the gravitational potential. But till then, thank you for watching.